bad. It's very hard to do it this way.
All right, so as they're popping in, welcome everyone. Thank you for joining us for today's workshop. We have Dr. Gary Halada, Associate Professor and Undergraduate Program Director for Engineering Science with us today. He's going to share more about the major and his role here at Stony Brook University. If you have any questions throughout the presentation, feel free to submit them using the Q&A feature. And so I guess without further ado, I'll turn it over to Gary for his presentation.
Okay, thank you very much. I will going to share my screen in a second. And I do want to say that if there are any people, if anyone has questions, I will try to answer them during my presentation as well. So you can just put them into the Q&A, and I'll get back to you on them, and hopefully I'll answer you correctly. I'm not sure. All right, let me share my screen. Oh, wait, I hit share screen and something funny happened. Okay, it's better now. All right. If since I cannot see your faces, so if you cannot see my screen for some reason, please write something immediately in the Q&A or in the chat so we can tell. So is there anyone who cannot see my screen? Give you a second. We see it. All good. All right. Thank you, Michael. Appreciate that. All right. As I mentioned before, or as Jonathan mentioned a minute ago, I'm going to talk a little bit about my department, the major that I'm in charge of, maybe a little bit about my research, random other things thrown in. Since I can just rattle on for a long time, just again, please feel free to stop me with comments or questions. I'm very happy to respond to those. My name is Gary Halada. I didn't put it on the screen, but I'm in the Department of Material Science and Chemical Engineering. I've been here for a while. I've actually been at Stony Brook a very long time, which may help if you have certain questions or maybe a point of interest. I don't know how many of you, or if any of you are yourselves Stony Brook alumni. I am a Stony Brook. I'm a Stony Brook alumnus. I got my degree in physics a long time ago. As my undergraduate degree, I actually had a minor in technology and society. Then I ended up becoming a graduate student at Stony Brook in material science and engineering. And from there, I just sort of stayed on. Then they won't let me leave. And please help. No, I'm very happy to be here and happy to be a part of what I see as a strong growth in the university. Any of you who are alumni may remember it from earlier times. But Stony Brook has continued to grow through thick and thin, and especially in the area of research and its influence around the world. Stony Brook's known in many parts of the world right now as a very high-level, excellent university, and I'm happy that my department and maybe me to a small degree can play a role in that. So as mentioned, my department, Material Science and Chemical Engineering, it was the first materials engineering department in the SUNY system. We have two ABET accredited undergraduate degree programs, the one that I direct, Engineering Science, and we have a second one called Chemical and Molecular Engineering, both from my department, which is, well, all these things are kind of impressive when you realize that we have about 18 faculty members. So we have to rely a lot on other departments to help us out. We have about 300 undergraduate majors, maybe a little less than that now, I'm not sure, in the two majors together. We take all 4 years into account. We also have a number of minors that come out of my department, material science, obviously, biomaterials, manufacturing engineering, environmental engineering, nanotechnology, and a minor called energy science, technology, and policy. And some of these minors were ones I started with National Science Foundation support, like the nanotechnology minor, and also the energy science, technology, and policy minor. We have probably one of the most prominent things about my department are our faculty. We're among the highest per faculty member research funding in the university. And it's, that's very important. And well, why is that a critical issue maybe for undergraduate education? It's because undergraduates have the opportunity to become involved in a lot of these different research areas. We have research going on in, for example, this is just what's currently going on, materials for fusion energy, battery technology, which is extremely important today, the ability to store power generated by photovoltaics or wind energy. That's one of the limiting factors to using alternative energy, is the ability to store the energy. And so obviously better battery technology is important. And you also realize it's important if you think about how important it is that you have to charge your phone and your tablet and everything else all the time. Having better batteries is extremely important. And it's a materials issue. And I'll get to why material science is so important and why that's a key feature of my department. Also thermal spray technology. I'll say a few more words about that as I go. It's basically a little bit, if you're not familiar with what thermal spray is, you might have some, it's similar if you have some furniture around, like outdoor furniture that's powder coated, that really good coating that doesn't come off and doesn't rust and, keeps your patio furniture looking nice. That's a little bit similar to thermal spray. It's a powder type coating, but instead of the way they apply normal powder coatings, thermal spray is a very high velocity, high temperature jet of material. And you can pour anything you want into that jet, almost anything. And so you can coat things with other metals, you can coat them with ceramics, you can coat them with all sorts of things. It's a great technology. First time I saw it in use had to do with the tail hooks that were used for catching, when on an aircraft carrier, when the plane lands on an aircraft carrier, in order to stop the plane so it doesn't go off the other end of the aircraft carrier, it has a hook that hooks into a cable across the deck. That hook obviously has to be very strong, very corrosion resistant. And at the time that I first heard about thermal spray at Stony Brook, they were coating the tail hooks for those planes for the Navy. We also have a very strong polymer group. Polymers, plastics, you might refer to them as, formerly known as polymers. And it's very important because obviously that is such an important part of everything in our everyday world. So many things are made out of polymers. Semiconductor crystal growth, that has a lot to do with the materials that are used for electronics. Or for everything from computer technology to communications technology. All these involve the use of semiconductor crystals, which I have an interest in that area as well in terms of my research, but in a little bit different sense, and maybe I'll explain that a little bit later. Sustainability, we have a strong group in environmental materials. That's an area that I'm personally very interested in. I'll show you a brief 1 or 2 slides on my research in that area. It's certainly not a huge chunk of the research in the department, but it's one that I enjoy a lot and I see as very important. And additive manufacturing. Additive manufacturing, you may know it as 3D printing. 3D printing was a very exciting topic, a big topic over the last few years. It sort of has waxed and waned a little bit over time. I remember when I first started attending meetings to look into research on additive manufacturing with a New York State consortium that involved all the SUNY campuses, as well as some other colleges. When I went up to Rochester to look into additive manufacturing, at that time in the office stores, I guess, I don't know if it was Staples or Office Depot at that point, one of those stores, they actually had an aisle of 3D printers. You don't see that on Long Island very much, but there they did, and they really thought that everybody was going to have this in their home, and it would be everything. And it became a little more difficult to. There's a little bit of hype around that technology, but in manufacturing and in industrial use, there's a tremendous number of applications that are important. Especially making, say, custom items for dental implants or dental materials, making custom parts in aircraft, satellites, making materials for implants in the body and other places. Extremely important what additive manufacturing can do. And the bottom just says we have 18 faculty members right now as of last count. We just have one new faculty member added this year. Nidhi, she's involved in the computational work. We have 5 faculty, mostly associated with the chemical and molecular engineering program, 11 in the material science and engineering graduate area, as well as the engineering science program on undergraduate level, and 2 who work with both. And mentions, we have millions of dollars in research expenditures, which is always nice because it provides those opportunities for undergraduates. We also have 100 graduate students right now between our PhD and master's programs. So if people are interested in the graduate program, we have a very strong graduate degree program. And that just shows our U.S. News and World Report's latest rankings among material science and engineering departments and among chemical engineering departments. And we're working on getting those higher, but it's because we do so many different things. We're not completely focused on one of these. It takes a little time to build up. Let me see if I can advance my slides now without causing a problem. Come on. Of course not. Of course it won't let me advance my slides. Whoops. I have to close. Okay, here we go. Oops. Is this my next slide? I guess it is. Unfortunately, I had to close. Oops. Yeah, you can hear me being very klutzy with Zoom right now. I was trying to keep the Q&A window open. I'll see if I can, because it was preventing me. Let me talk a little bit about, before I talk about specifically about the undergraduate program, this is a good time just to talk about material science and what material science and engineering is. That's the name of my graduate degree. I have a doctorate in material science and engineering from right here, Stony Brook. And this little figure in the middle of your screen is really, the way we think about material science. I mean, to me, it's really the defining science of all of engineering, which makes sense that we have an engineering science undergraduate program, because in order to meet the needs in the world today, all the different there's needs being driven by the need for more energy, the need for sustainable materials, issues having needs associated with climate change, with population movement, with so many things, that with medical needs. The whole we had a lot of activity involving COVID-19 and coronavirus activity. All these problems that arise can be solved many ways. A lot of programming solutions, a lot of people developing apps, and also people developing new, whether it's computer technology or chemical or drug technology, but a lot of it has to do with materials and what materials can do. So the way we look at materials, basically, we think about the different types of materials, that the categories of materials that you see every day. Metals, you know what metals are. You know what ceramics are, like a dinner plate. Polymers, these are everything from rubber to hard plastics, all those things that you have to kind of find a tiny number on in order to figure out whether you can recycle them or not in the kitchen, or before you throw them out. These are all different. Those are different types of polymers. You see a little number and it says PP next to it, for polypropylene, or PS for polystyrene. These are all slightly different chemistry of long chains of carbon atoms. Basically, it's long chains of carbon atoms with different stuff hanging off the sides of it on a molecular scale, but it gives it completely different properties. And then combinations of these referred to as composites. For example, very expensive sports equipment. Just as an example, often you have very small graphite embedded in a polymer. So you have a graphite reinforced polymer tennis racket, or something like that. By creating a composite, you can take the best of different types of material and put them together. There's a lot of dental composites, for example. Your teeth have to withstand thousands and thousands, tens of thousands, hundreds of thousands of loading and unloading every time you chew on something. That requires the material to be strong but flexible, able to absorb some impact, not crack. this really requires you to put different categories of materials together to get something that works well. And then the question becomes, how do you then form that into what you want? So these different types of materials have different structures. They have different properties. And by processing, as I just started to mention a second ago, by processing these materials in different ways, heating and cooling and shaping them and adding other materials to them. For example, in electronics, you take other atoms and you dope them into a material to give it a different electronic property. These are all methods of processing. It's how you process the material. And as an example picture down here, I have it processing. This is actually a picture of a type of 3D printing, or that's used on an industrial level, primarily called laser powder bed formation, LPBF, okay? Or sometimes called SLS or SLM, which is selective laser sintering or selective laser melting. A lot of names for it. This is probably the most industrially relevant type of printing that can be used with metals or ceramics. And in this case, basically a laser is fired into a bed of powder. So you fill up this tank with powder, and you would shine the laser down into it, and the laser has a high enough energy that it actually melts the powder together a little bit into a shape. Now, that shape can be defined by how you use a mirror or something to move the laser light around. So you can basically draw the thing you want to make, and it melts the powder together in that shape. Kind of a simple way of thinking about it. And then there's a little platform underneath, a little elevator that moves up and down. It carries the powder up and down. So you make many different layers. And you can see on the right here's a picture of a laser hitting a powder bed, and it's forming these long shapes we call dog bones. They're for standard testing of materials. And then when we're done, you can take them out of the powder and you have your final product, unless you have to treat it somehow. Sometimes depending on how you made it, you might have to get rid of some pores, some porosity, and then you have to try to do different things to do that. Or you might want to smooth the surface, so you need to use some type of polishing steps or something else. And sometimes you have to, sometimes the parts get stuck and you have to cut them free and do all sorts of things. But that's a form of processing. So one of the things I study is what happens when you change the processing parameters. You change the speed that the laser is going at, right? You go back and forth the laser. I'm going to try a different speed. I'm going to go this fast or faster. How does that change the properties of the material? So how is the processing affecting the properties? And then I can take the whole thing, and using the tools of characterization, I've got a big fancy piece of stainless steel up here. This is the sort of thing that this is actually a picture from Brookhaven National Laboratory, and I'll mention them again because we work a lot with Brookhaven National Lab. We're able to use something like the synchrotron light source at Brookhaven, which is an incredibly powerful X-ray tool. And as you know, if you've ever lost something on the floor, the brighter the flashlight you have, the easier it is to find something. And Brookhaven National Lab, we're lucky, they have the brightest flashlight in the world. They have the NSLS-2, National Synchrotron Light Source 2, accelerates electrons in a circle and in a large ring, and I'll show you a picture of it. And when the electrons turn the corner, they release energy. And some of that energy is in the form of X-rays. And we can use that X-ray light to actually look at materials and see their chemistry and even their interatomic structure. We can use electron microscopes, another tool where you can focus electrons in order to see things much smaller than you could see with an optical microscope, to look at how the atoms are arranged. So we can use these characterization tools to see how this processing is changing the structure, which changes the properties. All right, so that's the story of material science. That's how it works, and it's been the same way for a long time. One of my new and unfortunately expensive hobbies that I picked up as a result of having to spend so much time just hanging out with my computer during the past year of COVID-19 I started poking around eBay, and I know people do that. And I started finding all sorts of interesting stuff. And I love history. I love the history of science. And so I just the other day I bought a lot of different historical items, and I can actually show you some. But one of the things that I found was an old article just last week. It was just delivered today. It's a article from 1759 that was published about a scientist who wanted to understand electricity, and he did not have these kind of characterization tools. This was around the same time that Benjamin Franklin was, putting a key on a kite string to see what that electricity in the sky was really, what it would do, what really happened. And this particular fellow, his name was Richard something, and I don't remember, I just got it. He was known as the Barefoot Philosopher because he studied electricity. Yep, if you have questions, please submit them in the Q&A. I might see them. He studied electricity by pulling his stockings off. And you know that if you pull off your socks in a dry room, you'll get little sparks. If you're raising your hand, I can't actually, just type a question. I think I would see it. So you pull off his socks, and the little sparks that he got, he decided that was his form of characterization. That's how he was going to study electricity, basically by pulling his socks off a lot. It's just, I got to read it. It just came today. I'm going to read it. It's got a 10-page paper on pulling his socks off, which I just think is going to be great, from 1759. Anyhow, let me, if you do have a question, yeah, please put it in the Q&A. It's the lower right corner of this slide, and I talked a lot about this one slide. I guess I didn't have to worry about not having enough slides because I've got too many. The other part of material science isn't just trying to get the structure right or the chemistry right through your processing and understanding it. Why are you doing this in the first place? And I got these three very different pictures down here. Just reflects certain material science that either we're doing in the department right now or that I've been interested in. You probably don't recognize, well, you probably recognize the upper right picture. We have one faculty member who's working on materials for flame retardant pajamas. Because a lot of the flame retardants that are used in children's pajamas are not the safest materials in the world. I don't know all of them, but some of the chemicals that are used, I'm not sure what they're, they work, but at the same time, they may not be chemicals that we'd like to replace them. I'm not saying they're dangerous, but we'd like to replace them with safer chemicals. So one of my fellow faculty members, Professor Rafalovich, she's looking at putting nanoparticles of clay into the polymers that are used to make pajamas and other things. And she has discovered that because of the interaction of the polymers and the clay, because of this composite material, the material is self-extinguishing. It won't burn. So it's very fascinating. So that's how we respond to a need. The picture at the very center at the bottom is a fusion reactor. It's about as different as you can get from children's pajamas, right? A nuclear fusion reactor that's being developed. And a problem with developing these next generation nuclear reactors, like a fusion reactor that doesn't generate waste, so it is a better in many ways as an environmental alternative. Are the materials that you have. The materials have to be incredibly resistant to high temperatures and high pressures and so forth. And so one of my fellow faculty members, Professor Trelowitz, he's looking at developing nanocrystalline materials that can be used in a fusion reactor. He's working with the Department of Energy and the US Navy and a number of other groups. The lower right picture I put in here because one of the areas that I'm interested in personally is the area of humanitarian engineering. That's, how can we help use engineering to help solve some of the humanitarian problems of the world? This is a picture of the Zatari refugee camp in, I believe it's in Jordan. I might get that wrong. But it's a refugee camp for people fleeing the Syrian civil wars. And it's the most crowded refugee camp, or one of the largest in population in the world. And we recently had a speaker here at Stony Brook by Zoom, Professor Ryan, who's actually looking into how to recycle the mattresses for a specific purpose, because that's something they have a lot of, are mattresses there. He a wonderful talk, and there's some articles about this in a documentary from the BBC. Polyurethane mattresses being recycled to form the basis of hydroponics, because many of the people in this refugee camp are farmers, but they can't farm. So there's also an issue of human dignity. What do you do when you can't do what you're interested in anymore? So he's actually been he's actually been developing better ways to use these polyurethane materials for hydroponics. And so there's another material solution, and that addresses both the need for food, the human dignity issues, and so forth. So basically, the needs drive the research. All right, anything from pajamas to nuclear reactors. They drive what we do, but we use the tools that we're familiar with. And one of the things I like about running the engineering science program is it provides a lot of opportunities for undergraduates to get involved in research, because material science to me is the core of engineering science. So let me move on to talk about engineering science. Whoops. Okay, so this is the program that I direct. It's actually the oldest engineering degree at Stony Brook. In fact, when Stony Brook first had an engineering degree, it was only one degree. There was no electrical, mechanical, and so forth. It was the BE in engineering science. So that's been around a while. I won't go into it. I can go into the degree in detail if you're interested in the courses, and I'm sure students would be interested in knowing what you need to know. It basically gives you a strong foundation in physical sciences, and by that I mean physics and chemistry, and sometimes biology. Biology is becoming a very important part of just basic engineering knowledge. There's an exam called the Fundamentals of Engineering exam that you have to take in order to become a PE, a professional engineer. And they test you on physics and chemistry. They've started testing on biology as well, because so much of engineering has to require some knowledge of biology, of what's at least important in biology. Also a strong foundation in mathematics, and by that I mean calculus, and sometimes linear algebra, statistics, data analysis, and engineering sciences. This is a quick question. The answer is yes. I'm majoring in mechanical engineering, but I also really like chemistry. Is it possible to use the skill set I gained from that major to get involved in chemical research? Yeah. As I tell my students, there's multiple ways to be an engineer. One is, based on the degree that you got. Another one is based on the job that you do. If you go back to the way engineering was taught a long time ago, they didn't have engineering degrees, and in fact, they didn't have engineering degrees at all in England, for example, before 1900. It's the way it was seen, that engineering was not seen as something you learned in school. Engineering was your job. In school you learned natural philosophy, you learned humanities, you learned these things, and then you applied that knowledge to a technical area. It's only been, in the last century that engineering degrees have grown in many places in the world. So the answer is yes. You can apply one area to another area depending on how much you can educate yourself. I often tell my students that the most important factor for success as an engineering student is self-efficacy. And so what's self-efficacy? Some people think self-efficacy is just your belief in yourself. I believe I'm a good person. I believe this, I believe that. But this is a special type of self-efficacy. This self-efficacy is about, I see your question, I'll get to you in a second. The self-efficacy I mentioned is your ability to find the information you need to solve a problem. And that's what our engineering degrees help you to do. I work with a lot of undergraduates in the lab. I'll show you a few pictures. I often talk to them about this. You're going to see problems you did not learn in class, all right, that are not in your textbook. How do you know how to solve them? And it's your ability to know where to find the expertise, where to find that book, how to, who to talk to. It's that ability to think through a problem. That's the most important thing you get from an engineering degree. Now, my sister was a dean of nursing at another college, and she said that in the nursing profession, very often for nursing school, they loved getting people who had studied engineering because they were good thinkers. They were good thinkers at how to think their way through a problem. Right, let me just majoring in computer science, but I want a minor in engineering. Sure, it's possible. You just have to see what the requirements are of the minor. I'll talk about that. Anyway, and then selected courses. And in engineering science, we try to give you a taste of other disciplines. So there's selected courses in electrical and mechanical and even environmental engineering. So, and that's important. It's so you can speak the language of these other engineering areas. If you study to become a mechanical engineer or an electrical engineer, some of your language is unique to that profession in a way. And it's important, say, if you want to go into project management or quality assurance or certain areas, that you can very easily work with these people from different areas. So that's part of what we bring into engineering science. Unique features of engineering science include flexibility. We have 6 specializations right now. I have a list of them coming up. I'll jump over to that slide in a second. So that gives you some flexibility in choosing your technical electives. And you don't just have to choose the ones that are there. If you decide that, had this happen a couple of years ago. There was a student who was studying something in material science, but they wanted to go take a course in geology. It wasn't in our list of approved technical electives, but they really wanted to understand high pressure mineral things or whatever. And it seemed perfectly reasonable to me. So I said, yeah, we'll use that course instead. So that we're flexible in our technical electives. And the other unique feature, and I'll mention that next, is student access to research. Quick question here. I like your questions better than what I'm talking about. Is it possible to do both? One is a major and the other is a minor. It happens all the time. Our program runs 5 minors right now. I help coordinate a nanotechnology minor. Those students come from every single major. They can come from anywhere. So yeah, sure, it's possible to do a major and a minor. We also have a popular 5-year program where you get a master's at the end of 5 years, a BEMS. In materials, you get the master's in material science and engineering. We have quite a few students who like to do that. I know I've seen, in fact, one student who works with me just entered that program, something you decide upon in your junior year. And you start taking graduate courses when you're an undergraduate, so you can fill it in. And finally, I just want to mention we have an excellent record of our graduates in industry, in academia, and in research. Especially having been one of the oldest engineering departments, we have lots of data on that, and we can point to a lot of things that our graduates have done, which have been very impressive in using the skills they learned here, and so forth. Let me go ahead. I forgot what's next. So. Good. Again, just talking about the engineering science major. What do our graduates do? This is just, if you get an undergraduate degree and you go right into the work world. Well, you can go directly into graduate programs, first of all, in things like material science, chemical engineering, process engineering. There's something called that, manufacturing engineering. Really, any of these areas, this is a good background for. A number of our students have gone into technology management, because obviously if you have this broad background, that helps. Quality control, process engineering, failure analysis. So one of the courses that I teach is something called Learning from Engineering Disaster. And I like teaching by using things that blow up and disasters, because things that failed, because engineers learn so much from those. But to understand them, you need a pretty broad background in engineering. The people who try to understand why a plane crashes have to be able to see it from the point of view of mechanical engineering, aeronautical engineering, electrical engineering, computer engineering. They might not know all those things, but they need to know how to assemble an effective team and then get all that information and put it together to answer, coherently. They're kind of like a detective, like a detective of, the Sherlock of engineering failure. Can you see what happened? Can you understand it based on what, all these different things that you've collected, all this information? Industrial engineering design, materials engineering. Obviously, a lot of our students, I'll show you the names of some of our companies that students go to. Systems engineering, manufacturing engineering, project management, technology assessment. Very important. If you want to assess possible dangers or risks from technology, it's good to have a broad background and especially ability to understand materials. That's very important. We have a number of people who have gone to patent law, also as a pre-med program. It doesn't say that here, but I know we have a bunch of students who've gone pre-med. Science and technology, policy development, risk analysis, technical writing. These are all a lot of things that students do if they're getting a job immediately upon getting their undergraduate degree. Again, many of our students go on to graduate school, even for 1 year or more. We have quite a few who've gone on to PhDs. In fact, one of our most successful faculty members right now was an undergraduate in this department. And I know because he used to sit next to me on those open house days when people would come around and ask what engineering science is. He'd be the student sitting next to me. And he went to get his PhD at MIT, and now he basically is our best funded researcher in my entire department. It's amazing. This is scary, but anyway, it's you can go on to do a lot of things. These are just a quick graphic that shows the name of the companies that our students have gotten jobs at over the past 5 or 6 years. You can see this is all over the place. It's a wide range of things. There's companies that are specifically focused on materials like Applied Materials or Flame Spray Incorporated, Chromaloy. Well, my research, how much patience does it require? I'm not a very patient person. Usually we discover new things one after another. Do you work on something and mull on it for a while and then suddenly find something surprising? Well, yeah, yes. It's some things were discovered by, I discover some things by accident. Sometimes I have to go back and look at old data because something doesn't seem right or seems weird, and discover something that way. Sometimes I discover something, I get really excited, and that I realize I made a mistake. I didn't discover anything at all. So in that way, you have to be able to. One thing that research requires, like any job, is your internal personal ego resilience. I think you know what I mean by that. I remember taking a result to an engineering conference and talking about it and being all excited, and then later on I figured maybe this isn't quite what I thought it was, and you can't so that's another opportunity just to learn more. It's really important that in terms of research that you're able to question yourself. Right? I'll show you an example of my research next. I'll talk about it. Let me do that because we don't have much more time. So I just want to, if you're interested in this major, in this area, just trying to show you that these companies are very different. Boeing is very different from Kimberly-Clark, right? I don't know if anybody's familiar with, you've heard of Boeing, right? You've heard of GE, for example. Kimberly-Clark, what do? I mean, go down the paper aisle of any store. Look at all the tissue and toilet paper. A lot of it comes, even though what brand name it has on it, it's coming from Kimberly-Clark. They make paper stuff, everything out of paper. And that's a material science issue. Again, the performance based on the properties, based on the processing. Companies like Applied Material, they're all about electronic materials or materials for fusion reactors even, or pipelines. Some of these companies, like say Walden Environmental Engineering that recruits in my department, they're interested in students who want to study environmental engineering or want to work in environmental engineering with a materials background, because so much of environmental engineering is on the effect of materials in the world. Especially, for example, pollutants. So, and also, design of systems, because our students do take courses in systems engineering. So they have to learn how to, say, design a sensor system to understand, if this coastal, water level changes, how's that going to affect the movement of pollutants in the environment? That's something that a mechanical engineer could do, but it's also an engineering science student is very good at that. Some of these companies like Flame Spray Incorporated are companies that grew out of our department, because that came out of the thermal spray laboratory, which has been in operation a long time. Thermal spray is I believe, currently the largest single laboratory, the largest single laboratory on campus here at Stony Brook, not counting the research park across the street. Some of our students work at Brookhaven National Laboratory. Some work at some of these places that make standards like ASME or ASML. Some that do electronics and computer research like IBM, Motorola. National Grid is an energy company. Amoresco is both energy and sustainable building. The Wood Group is all about sustainable development, also energy. Northrop Grumman. All right, some of you might recognize General Dynamics, Electric Boat. They make nuclear submarines. So, Dayton T. Brown is a testing company on Long Island, down in Bohemia. So the people know where that is. Corning, we've heard of. BAE Systems is another company that makes military hardware, but also transportation systems. They make electric vehicles, for example. So this is just a sampling. Okay. Let me just go on the next slide. As I mentioned before, a lot of our students, if they don't go directly into, don't go to work for a company, they also go to leading graduate programs, including Stony Brook, like me. But they've gone on to, as I mentioned, one of our fellow faculty members who was an undergraduate in engineering science went to MIT. This is just the last few years: Berkeley, Northwestern, Columbia, Harvard, Penn State. Also, international universities: National Chongqing University, China, Cornell University, McGill University, Purdue, Berkeley, and so forth. A lot of these are graduate programs in materials, graduate programs in just other forms of engineering, chemical engineering, even graduate programs in physics occasionally. So nuclear, we have one of our students went to a graduate program in nuclear physics at MIT. That's where she went. So anyway, this gives you some idea of the types of places people go. So I don't have time to sit on this. I just, if you look through LinkedIn and you look for our department and so forth, you can find so many students who graduated from our program and what they're doing now. So if you're interested in finding out more, here's Priya Datta. I remember her. She's at Whirlpool Corporation. She's a product development materials engineer. Here's Chantal. I remember her. She's in the area of material processing at Boeing now. She was an undergraduate in our program. Oops, there you go. Oh, Lacey Schwab. I hear from her occasionally. In fact, I heard from her recently. She's at GE Power, a part of General Electric, in the South Carolina area, doing power systems. She worked in one of the labs in the department, the Engineered Metallic Nanostructures lab, downstairs, right on the first floor of the engineering building. Let's see. Dema, he's at Sikorsky Aircraft up in as a manufacturing engineer up in Connecticut. Miranoir, I remember him. He did a lot of different things. He's a project engineer at a small company, Sigmund Kohn. He does mostly manufacturing of precious metal products in the aerospace, medical device, and semiconductor area. This is obviously a while ago. He's still there though. And so he does, again, materials engineering, but he does it at a company that handles many different types of projects. Alicia Elliott, she's the one I remember who's currently in the graduate program. I think she's just graduating this year with a PhD in nuclear science and technology from MIT. She worked in my lab, so I remember her quite well. So it's, again, and she worked with nuclear materials in my lab. When she was at my lab, I was still working with Department of Energy on nuclear waste. And so she worked on a nuclear waste issue. So anyway, just to give you an idea of some of the students. Oh, Ted Feldman. I put him here because he sends me a Christmas card every, he's actually graduated now. He was in the PhD program at Harvard and MIT. Not one wasn't good enough. And he was studying medical research, all right, medical materials and medical physics was his area. So I'm not going to linger on this now. Oh, right. And Kristen Scroop, she's the person at Walden Environmental Engineering. She has hired a number of our other graduates who want to work in the area of environmental engineering. So if you just go to LinkedIn, I can show this because it's all public knowledge. You can actually find out many students who have gone through our program and what they're doing today. If you have questions, I can always refer to that. I'm not going to go through the whole program because I don't want to spend time on this. I just want to I'll talk about my research for the last 10 or 15 minutes here, or some of the research going on. So this just shows all the courses you'd have to take in engineering science, and pretty much what I've already mentioned. So I don't want to linger on this, but I do want to mention that there is a core program that's strong in physics, chemistry, calculus, a little bit of programming, and then a lot of these sort of engineering science areas, various laboratory courses. There's my class, Learning from Disaster. I also teach the Introduction to Engineering Science. So if you do join our program, I'll definitely see you. Senior design is always very important. But as I mentioned, courses in electrical engineering, like electrical circuits, mechanics of solids, and mechanical engineering department. So you do get that broad background. Environmental engineering, for example, and all those different engineering sciences you need, like fluids and transport and systems engineering. So this is, we try to create this program in such a way that it brings the different areas together with a very strong focus, though, on materials engineering, which is the primary engineering science that we've created our program around. And I mentioned there's specializations in our program as well. So that's part of the flexibility in it. Biotechnology is one of the specializations. Now, these specializations are different than the majors. You could major in biomedical engineering. The specialization is just a core of 4 courses selected carefully, 4 or 5 courses, to give you a depth of knowledge in one area. A little bit like a minor, but not quite. Electronics engineering, so you take courses in electrical materials and how to design things in electronics. When do I need to select a specialization? 3rd year. How are they supported if they want to go on and do a PhD? I didn't realize this was in the chat. I got it. How are they supported? If they want to do research, they might get paid. If you work with a laboratory, you can be supported, and certainly students who go on into actual graduate research will be supported with a graduate research, support, the normal support you might get. You can also get supported as a teaching assistant while doing research. Mechanical and manufacturing, material science, engineering management, civil engineering, environmental engineering, nanoscale, but again, they're different from any majors that have these titles because they're not all just focused on that. It's a broader background in those areas I showed you with a focus in one of these areas just to give you some strength in that area. So when you go for a job someday or you apply to graduate school, you can explain this on your application. And we write a lot of recommendation letters around here. Okay, I said it's very important that you get involved in some way in an internship or into research. And it's pretty much that's part of all these specializations. So it's very almost not, I wouldn't say required, but it's something that's very important. But it's more or less required. So I'll just talk a little bit about my own research. I think someone's trying to ask a question, but if you're raising your hand to ask a question, the best thing to do is type it. I have a, whoops, hang on a second here. I have problems here. I didn't lose the slides, did I? Because I have a little strange orange window on my slide now, and I don't know what it is. Please move this window away. I don't, okay. Sorry. All right, it's going away on its own, whatever it was. Oh, can you talk about your internship program and studying abroad? I don't know much about studying abroad. A few of my students have studied abroad, which is fine. The university has a good program in that. I'm not the one to answer that question. Internship programs, our students most of the time actually find their own internships. I just then help coordinate their reporting for the purpose of getting credit in the internship, for the internship. And I can also, a lot of companies call us and say, we have an opportunity. If it's research, for example, the students you see in this picture here was my grad student, Mike, who looks like a grad student here, staring blankly into space. But these are students who are working, undergraduates working in my lab, the surface analysis and corrosion science lab. How did they find this position? They basically wandered in and talked to me. They said, I'm interested in doing something. And so I said, sure, come by the lab. Let's see what we can do. So they were involved in a couple different projects, two major projects that I've had in my research over the past couple of years. One is in the area of sustainable materials, and one is in the area of 3D printing. So in the, I'll show you now, okay. This is just a little summary of research project that I've had. I'm working with SUNY FIT. All right, that's the Fashion Institute of Technology. As you can tell, I'm not very fashionable, but I work with the Fashion Institute. I also have worked with the National Research Foundation of Korea and Chungang University in Korea on this. We're looking at ways to more environmentally recycle clothing. That's a material science problem. Clothing industry is one of the most polluting in the world. It says predicted by 2030, almost 150 million tons of fashion waste. The whole fast fashion area, right, is kind of do faculty in the department work with undergraduates? Yes, I just showed you some. In fact, the textile industry is responsible for 10% of all global carbon emissions. We worry about climate change and where that carbon's coming from, and almost somewhere between 15 to 20% of global water pollution. So much water gets used in the production of textiles. In fact, it's somewhere it says how many gallons are used to make one T-shirt, which you buy in Walmart and throw away. So the idea is to create textiles out of non polluting materials. And the folks at FIT actually have a company called AlgaKnit that's working with algae and using algae. They had on display a pair of sneakers made with algae. Interesting. But there's a lot of interest in this idea of green recycling of textiles. In fact, there's interest from major fashion designers around the world. Stella McCartney, for example, is actually an environmental consultant for H&M, one of the other major fashion manufacturers in the world. But there's a great deal of interest in being able to do recycling of clothing, for example. And one of the things that I've worked on with FIT and with some of the research that I do is to create a greener process to basically take fiber that's part of waste material. And I'm just starting out with simple cotton textiles, muslin cotton textiles, and then using a thermochemical process, heat and chemicals, but mild chemicals, try to make the fibers deweave so that they can be remade back into raw materials. And so, in this process, this shows the work I've been looking at recently. We're working with waste textiles from the fashion industry, getting them from FIT. This is the muslin cloth that's used in making dress forms, and they throw out tons of it themselves. So I take that cloth, and then we have a process where we treat it with simple chemicals like citric acid, basically orange juice, right? mild sodium hydroxide solutions, urea, which is a mild enzyme. And we're learning how to take that and then very quickly, hopefully, turn it back into the sort of cotton you would weave the fibers from. So it can go back into a carding and weaving process. So I only know these words because I work with fashion people at FIT. And what's important about that to me is that, is that down the lower left, you see cotton fiber down here. Cotton fiber is an incredibly complex structure. I didn't think about this before. I didn't even know about it before. So you're wondering how we discover stuff. Well, sometimes it's just discovered in the accident of research. So cotton fiber has multiple layers. Each layer has a certain amount of crystallinity of the cellulosic molecules. The cellulosic molecules join to form nanofibrils inside. It's an incredibly, intensely complicated structure that has nano and micro scale structure to it, has chemical structure. So I'm actually using tools at Stony Brook and Brookhaven National Lab to understand if we can break this material down into individual fibers without a lot of effort, but maintain this structure, because this structure is what gives it its strength. If we had to make this structure from scratch, that's very hard to do. Imagine trying to make one material inside of another material. That's not easy. All right. And yet nature does it so well. All right. So we want to maintain the strength, and then we want to look at, can we recycle textiles that are dyed? So it gets even more complicated. So before I run out of time, let me show you one other area of research I'm doing. So this is work supported by the National Science Foundation and also the National Research Foundation of Korea. The other area that I'm working with, the fellow I'm working with on this, Jason Cholowitz, he's the one I mentioned before who was an undergraduate in our program and now has the biggest program of any of us in our department. It's amazing. Working on this with folks from Stony Brook, Penn State, Johns Hopkins University, and Brookhaven National Laboratory, among others. This is with that 3D printing of metals. I showed you the process before. This is, I don't have a chance to show you very much, but for example, this is a 3D printed metal. This is 3D printed 316L stainless steel. This is steel that gets used in all sorts of interesting applications. I have lots of pieces of it here, some more complex than others. And I'm trying to understand essentially what's affecting the rust of this steel. Now, my PhD thesis was in corrosion, was in rust. I am a rustologist, I guess. I study how materials degrade in the environment. Now, if we can understand how they degrade, what's the process of localized corrosion, also known as pitting in this case, how is that affected by the powder that we use, the process we use to make that powder into what I just showed you, and how can we use characterization tools? It turns out that when you hit something with a high power laser and you heat and then cool it very fast, you get this nanostructure that forms inside. And that nanostructure actually shows differences in chemical composition from one point to another. That's really important for rust, for how something rusts or it doesn't rust. So that's why I'm interested in that. And then can we take that knowledge and use it to make a better material so that you can use, they want to put 3D printers on ships. They want to put 3D printers, in the field with tanks and be able to repair the tank if it breaks down in the field. It's very important information. The Navy is funding this work. And of course, the Navy is extremely interested in this. And we're using not just tools at Stony Brook. So for example, you can see here's some of that printed metal I just showed you. If you put it under a microscope after etching it with acid, you see the actual print pattern. The little particles are melted together as the laser moves back and forth, almost like a weave. It reminds me of my woven cloth again, except now it's steel. And if you take a look at this under an electron microscope, you can see this nanostructure that forms. We also see that structure forms when it rusts inside the pits that form on the surface when it rusts. So we know it might be important. So then we can turn around and use those techniques at Brookhaven National Laboratory to look for the nanostructure that forms inside and look at these chemical differences, because those techniques using the X-rays at Brookhaven can tell us what different elements are present where and what states those elements are in, whether they're oxidized or they're not, or whether they're reacted with sulfur or something. We can tell that through using the tools at Brookhaven Lab. Oh, by the way, I saw this just popped up on the Stony Brook website, so I have to. I will congratulations to my colleague Jason Trelowitz, who I just talked about. He was named one of the Power 25 in Education by the Long Island Business News. His work is on fusion energy research, but also helping me with this 3D printing stuff. And we do a lot of work with Brookhaven National Lab because it's not far away. It's right down the road from Stony Brook, basically, half an hour drive, or depends how fast you drive, I guess. But anyway, the facilities there that I tend to use a lot are the Center for Functional Nanomaterials, which has amazing microscopes, and the NSLS2, which is that synchrotron source. And you see that big electron ring here. By the way, if you want to know how big this building is, you could take Yankee Stadium and drop it right into the middle of it. It would just fit around it, like a nice ring around Yankee Stadium. So the new Yankee Stadium. So now you know how big that building is. And it's full of high-tech research equipment. And I try to share that research with my undergraduates. So they haven't been able to go to Brookhaven lately because of COVID, but we'll get back to that point very soon. Okay. Just about out of time. Let me see one or two more quick things I want to mention. A quick question here from somebody. Do you have any advice on how you get started in research in high school? Things I can be prepared for once I begin engaging. Okay. Oh, you've got a live answer from Jonathan. Do you want to speak?
No, sorry. I was just indicating that basically you were going to answer it live so that he didn't expect a text response.
Oh, okay. All right. Thanks. All right. I'm live and I'm answering. What can you do in high school? Learn to find information. I've had this advice. One of my students who is doing research with me right now on electrochemical printing, which is a new technique, said, he wished that he had learned how to be more bold in asking questions. It's good that you're asking a question right now, but sometimes you can write to scientists. You can write to people in these laboratories. Get used to that. Get used to reaching out and finding answers to things. That's really important. I wouldn't say just study one area or another. Obviously, have good grades and learn how to study. Learn how to learn. That's very important. But learn how to teach yourself. Because a lot of times you're not going to learn something in class that you need to know. So be used to the process of finding a book or finding a website or finding a YouTube video, find whatever, and teaching yourself something. The way you would teach yourself how to cook something if you didn't know how to cook it. You don't necessarily wait for somebody to come and teach you. So learn how to take control of creating your own knowledge. And that will serve you very well when it comes to college. That rhymes too. I didn't mean that to rhyme. Anyway, that's 5:04. So let me see if I don't really want to spend too much more time with this. I'll show you a few pictures. There's me in the back. This is taking some students over to go back to the Center for Functional Nanomaterials at Brookhaven Lab. And you see they're very happy. They like going over there. I also took a high school teacher with me. If any of you are high school teachers, please get in touch with me. I like to also provide research experiences for high school teachers. Some of the other folks that have very large laboratories and researches in my department. My research is pretty small, but this is Esther Takuchi. She has a very large center called M2M, the Center for Mesoscale Transport Properties, between Material Science Department, Chemistry, and also Brookhaven. And she studies battery systems. And she's also has, I believe, over 160 patents to her name, including patents for pacemaker batteries and things like that. Yes, I'll show you my email in a second. I'm going to put it up on the screen. I'm sort of jump to the end here. I don't want to show you everything in the world. This is another one of our large labs, the Center for Thermal Spray Research. There's Professor Sampath, and many of these are undergraduates who work with him. And they actually look at this super fast, super hot spray of jetted material that you can coat anything with in order to prevent it from wearing away or corroding. It's brilliant stuff. And I mentioned the Garcia Center for Polymers and Engineering Interfaces. Maybe some of you were in the summer program with them. Every year they work with high school students. I bet there's some of you who may have been in it. I don't have a podcast. If you want to, oh, it's right. Yep, and there's oh, you're sending. Okay, and the recording. Oh, all good stuff is coming up. All right, I'm going to wrap this up. And by the way, just to mention, the Center for Polymers and Engineering Interfaces, they've been working on better face masks as an example of work that they've been doing. Oh, and look, I got to my last slide anyway. And with my email on it, how can you contact me? By that wonderful email at the top of the page, gary.halada@stonybrook.edu. That's basically my summary of this. Engineering science, a flexible student-focused engineering major, broad range of opportunities for graduates, world-class faculty and research, as you've seen. And we also have these other programs, the chemical and molecular engineering program, 5-year BEMS programs, also our master's and PhD programs in material science and chemical and molecular engineering. And with that, I'm done. So if there's any other questions, I'm very happy to answer them. Or if anybody else wants to come on and say some words from admissions, or go for it. I didn't even get to show you my. I have a. This is a rivet from the Titanic. I forgot to show you that. And my piece of the Hindenburg. Okay. I've got a lot of junk here.
Well, thanks a lot, Gary. I hope the students enjoyed that as much as I did. I was over here laughing most of the time, even though I was on mute. I really enjoyed your presentation. And for the rest of the students, if you have any other questions after the event, feel free to send us an email or give us a call. And I hope you guys enjoy the rest of your day.
Yep. Thank you all very much.